In this next problem, we have two blocks, again connected by a pulley, but we see that now block A is on a flat horizontal surface and block B is on an incline. Let's say we were given this angle of the incline of theta. I forgot to draw that in my picture. And let's treat this problem as though the coefficient of kinetic friction for block A on this flat part and the coefficient for kinetic friction for block B on this slope are different. So maybe the floor and the slope are the same material, but the two blocks are different materials. That would cause different coefficients of kinetic friction, just to see what that looks like when we solve our problem. So again, we're going to start with a free body diagram, a force diagram for block A, and Newton's second law equations for that. And then a force diagram for block B, and the Newton's second law equations for that. If you wish to try it on your own, try to write those now, pause the video, and write both the force diagram and the equations for A, then the force diagram and the equations for B, and then I'll end up giving you the answer for A. I'll leave the algebra to you for this one. So let's look at a force diagram for block A. Block A is pretty straightforward. We've seen this force diagram before. We have tension off to the side here. We have a friction force, whoops, my arrow didn't make it all the way, a friction force for kinetic friction off to the left. We have a normal force up, and we have the weight force down, F, G, down. My Newton's second law equations are again going to be things that we've seen before. Let's take this direction to be positive x. And the x direction, sum of forces in the x direction, I'd have a tension force minus a friction force. That's a kinetic friction force. So that's going to equal the tension force minus the coefficient mu sub k sub a, because I've specified block A and block B as having different coefficients of kinetic friction. Then times the normal force. I know my normal force is just going to be mg because I'm on a flat surface, so I'll just write that in now, ma times g. And then that is going to equal my mass of block A times my acceleration in the x direction. I guess I could still write that. Again, the y direction, my sum of forces is going to be Fn minus Fg. We've seen that so much I'm not even going to include that. Then for block B, now again here we have an incline, so I would encourage you to note that incline on your diagram. So we'll have a downward weight. We'll say that that's Fg of B, and then we're going to have a normal force that is going to cancel the y component of that, because again we'll probably choose this to be positive x because that's the direction of our acceleration down the slope. So our normal force only has to counteract the y component of, let's do that in this color, right, Fg sub y, right? That's as big as the normal force needs to be. Now I actually have two forces pulling me back in this case. I have a, whoops, let's have that be black. I'm going to have my friction force, F for kinetic friction, but then I'm also going to have my tension force. My tension force is pulling back on me as well, Ft. Now, again, I've drawn these two forces. They look like they would sound to be bigger than that, so they should really draw them smaller, perhaps. Perhaps they're both smaller, but we get the idea that two forces are holding me back. Only the x component of the weight here is pulling me forward. So let's write that in our equation. We're going to have our equation as, let's just give you a second to look at that force diagram. I'm actually going to delete it in order to write my equation, but the equation is going to be based off of this picture. Let's actually do the following. We'll skip that, and I want to be able to go back to it. So I am not going to delete it. I'm going to write my equation now based off of that diagram. So my sum of forces in the x direction we had the G, the gravitational force, the x component of that, minus my tension force, then minus my kinetic friction force. That's going to be equal to mb times the acceleration in the x direction. That's my first equation. Then my y equation, Fy, I'm going to have my normal force minus the y component of Fg, my gravitational force, and that's going to be 0. We're going to say that it's not going to move up or down off of that axis. I know that I'm going to need the normal force in here for my friction, so I'm going to work with this one first and say, okay, my normal force is just equal to the y component. That's going to be mb times g times cosine of theta. So that's going to go in here, right? Mu b times my normal force. And then my x component is going to be mg sine theta. So this first equation here, right, this bad boy is going to come down here, and I'm going to say that my useful equation in the x direction is going to become, let's see, what would we get? We'd get mb times g times the sine of theta minus my tension force minus mu k sub b for that second surface. I can make a neater b. Sure I can. B times my normal force, mass of block B, times g times cosine of theta, and that's got to equal mb times a. And that is in the x direction. I suppose that's what I have for the first one. So now this is going to be my other useful equation. I'm going to pair that one with this equation. I've got two equations, two unknowns. So this equation combined with this equation in the box here will give me this for my acceleration. So if you work your algebra, you should get this. There are several lines that get us there. It's not anything that difficult. It it just looks something like that. When you get there, you see I made a few mistakes, but you should be able to do that yourself. I'll leave that up to you. I suppose now you could pause the video and look at it, but it's way more sporting and fun to give it a try yourself.